Hey there, welcome to today's lesson. Today we are going to see how to use the op-amp as an integrator. Let's look here. For an inverting op-amp, the feedback resistance is connected between the output voltage and the input terminal, which is connected to the inverting terminal of the op-amp. To convert it to a integrator, we have to replace the feedback resistance with a capacitor, and by replacing it with a capacitor we can get an integrator circuit. Now let's see. Here the current that's passing through the resistor R is IN, and the current that's passing through the capacitor C as IC. Now the capacitor is connected to the feedback, so let's name the capacitor as CF. Now the potential at this end is 0 due to the concept of virtual grounding. Now if we see, now by applying KCL, we can see by applying KCL, we can see IN is equal to IC, IN is equal to IC, where IC is the current passing through the capacitor and IN is the current passing through the resistor. For IN we can calculate it by Vin minus 0 by R, which is equal to IC, where IC is equal to, we can calculate IC by IC is equal to C dVc by dt. We know Q is equal to C into V, Y is equal to dQ dt, and where we get at constant capacitance C, I is equal to C into dV dt. Therefore IC is equal to C dV dt. Current passing through the capacitor is C dV dt. Now C dV dt, where dV is the voltage, where dV is the voltage across the capacitor. And by simplifying the above equation, we can get V in my R is equal to C dV by dt, dV dt, where dV is the voltage across the capacitor. Now we can write the equation as V in by R is equal to CF into ddt 0 minus V out. By further simplifying, we get V in by R is equal to CF, that is feedback capacitance, into ddt of minus V out, By further simplifying it, we get, and by arranging it, dV out by dt is equal to minus 1 by RCF into V in. And when you use integration on both sides, that is by integrating both sides, V out function of time is equal to minus 1 by RCF integration of V in as a function of time dt. Here we are assuming that there is no initial voltage, there is no initial output, and if we consider an initial output voltage that is present, then we should be adding one more term, we should be adding a V out 0 plus. This is the initial output voltage. This is the initial output voltage before we start the integration, if any output voltage is present. Now for RCF, the RCF gives the integration time of the integrator, Now, so using this circuit, using this equation, we can actually integrate any input signal. That is given to us. If we pass, now let's take an example. If we pass 1 volt of DC signal, to the input, then at the output we get this signal. Here you can see initially the output will increase, the slope will increase in the negative direction, and then after a point it will saturate after a point, because the output voltage cannot go beyond the saturation limit, right? Now here the rate at which the output voltage, now here the rate at which voltage output voltage gets saturated depends. CF is the feedback capacitor connected between the input terminal and the output terminal, and resistor R is connected in the inverting input terminal. So by changing the values of C and F, we can change the slope. We can change the slope of the output. We can change the slope of the output waveform. Now let us check an example of a sinusoidal signal, or a sine omega t. Now for sine omega t, if we apply an input voltage of sine omega t to the input, then at output we get a cosine waveform cos omega t. Similarly, for a square wave, applied at the input terminal, we get a triangular wave at the output terminal. Likewise, here also the values of the amplitude depends on R and CF, and by changing the values of R and CF, we can change the amplitude of the output signal. So by using this simple circuit, we can actually integrate any input signal that is given to our OP amplifier. Now V out, let's recall the formula once. V out is equal to minus 1 by CF into R times of integration of V in dt, where no initial output voltage is present. This is what we learned today.